Welcome viewers to this course on microscopy, where I will introduce you to different aspects of microscope as well as different properties of light. Now, before coming to light, actually I should tell that microscope, the source of illumination can vary from visible light to electrons. So today I will focus only on light microscopy, and a light microscope is an instrument which can be utilized to magnify objects which is not visible by our naked eye. Now, before delving into the details of light microscopy, let me give you a brief on light, especially visible light. Now, visible light is an electromagnetic wave, a term coined by Sir James Maxwell, where he told that it is made up of two components. As you look into the figure, you will see that there is an electrical component which vibrates in the x direction, and there's a magnetic component which vibrates in the y direction. The propagation of this wave actually happens perpendicular to both these directions. So this wave nature of light can explain certain properties of light when it interacts with matter. However, this wave nature cannot explain all the properties of light we see in our daily life. For example, what is the energy content of light? For this, the particle nature or the quantum nature of light is important, and hence light is actually thought of to have a dual character, a particle character as well as characters of wave. Coming to the particle concept of light, it is believed that light is made up of quantum of energy, and each quantum is known as photons. Now, a simple relation exists between the frequency of this light and the wavelength. If nu is the frequency of light and lambda is the wavelength, then it is related by the equation nu is equal to c by lambda. Again, when we know the energy of each photon, if capital E be the energy of a photon, then E is equal to h nu. Now h is known as the Planck's constant and nu is the frequency. Now combining these two equations, we can tell that E is equal to hc by lambda, where h is Planck's constant. The value is 6.62 into 10 to the power minus 27 arcsecond, and c is the velocity of light in vacuum, which is 3 into 10 to the power 10 centimeters per second. Now, if we know what are the wavelengths of light, what is the wavelength of visible light? Now, visible light is a part of the electromagnetic spectrum, which varies from the X-rays to the radio waves. The wavelength of X-rays can be few nanometer, and that of the radio waves is few millimeter, while the visible spectrum, that is the spectrum which we can perceive, which is the VIBGYOR, varies from 400 to 700 nanometer. So what we see is a very small part of the whole spectrum. Now, in case of light microscopy, it is this visible spectrum which is being utilized.
Sir, what are the wavelengths related to different colors we see?
This you can look at the table, which shows that the wavelengths vary with color. Now, human eye can perceive only the colors which I told you, that is in the visible spectrum, because the pigments in the eye can only sensitize these colors. Now, the sources of visible light can be solar radiation, that is sunlight, or it can be incandescent bulbs or even your fluorescent tubes, which can be used as sources in light microscopy. Now, before I go into further details about light, we should actually introduce you to the quality of light. Now, the quality of light means that what you see, what are the colors of light, how is light coming to your eye, whether it is coming from a single direction or not. Based on that, we can actually categorize light first depending on color. Monochromatic and polychromatic. Monochromatic means light of single wavelength or single color. Polychromatic means light consisting of different wavelengths or different colors. Next, we go on to another category of quality where we depend on whether light comes in phase or not in phase. So what do you mean by in phase? Now, in phase light can be considered when a light beam that is consisting of different rays of light coming from a source travels through a medium where the crest of one beam or one wave actually matches with the crest of another wave, and similarly the troughs of another wave matches with the troughs of another wave. So this is known as coherent light. Now, a non-coherent light, as you can know from the definition, does not follow this rule. Coherent light sources are very good for illumination and they can transmit their energy properly when they interact with matter. Now, coming to the direction of propagation of light from the source, it can be categorized into collimated and non-collimated beam. Collimated beams are those light rays which are coming in a single direction, parallel to each other. Non-collimated beams move in different direction. So, if I want to have a focused light, a collimated coherent beam is the best source of light. And this can be nowadays obtained using lasers, which I will introduce you in the later part of this course. Now, the fourth category of light is whether light is traveling in all directions and vibrating in all directions. This is what we call non-polarized light. Polarized light, on the other hand, the waves, especially the electric component of the wave, vibrate in the single direction. Now we come to the properties of visible light. We want to study these properties when light interacts with matter. So when light interacts with matter, it can actually cause reflection, refraction, diffraction, dispersion, and various other phenomena. So coming to reflection, when light interacts with matter, it can get reflected into the same medium, that is, the angle of reflection is equal to the angle of incidence.
Sir, I have a question. Are all the light that are not absorbed reflected?
Coming to your question, the answer is no. Not all light which is not absorbed is reflected. Some can be scattered, that is, it can go in any direction. Now, I should emphasize, coming to reflection, that here the angle of incidence should be equal to the angle of reflection. Even reflection by itself depends on the interacting surface. If the interacting surface is smooth, then it forms a type of reflection which is known as specular reflection. If the interacting surface is rugged, then it forms another type of reflection which is known as diffuse reflection. Now, not only that, there are other phenomena which happens if light interacts with matter. That is, the light ray can actually pass from one medium to another. This is known as a refraction, where the ray gets deviated from its original path when it's moved to its new medium, or the medium of refraction. Now, what determines whether the ray will deviate or not? It is the refractive index of the media concerned. If the refractive index of the medium concerned is same, the ray will not deviate. So what is refractive index? Refractive index is defined as a ratio of speed of light in that medium versus the speed of light in vacuum. So the refraction actually can happen from one medium to another. Now there can be two cases: when the light ray passes from a denser to rarer medium, and another when the light ray passes to a rarer to denser medium. So let's take two practical examples. Now when light moves from glass to a medium which is air, then because it is moving to a lighter medium, the refracted ray will get deviated further away from the normal. However, if it's the other way around, then the refractive ray will actually not get deviated, rather deviated towards the normal. Now, why is this happening? This is happening again because the velocity of light in these two medium are different. Now, what are the consequences of such refraction? The consequences of refraction is mirage in the desert, or if you can dip some sample in water, you will see that there's a change in the position, or what we call the apparent position of the object in water. So this happens due to refraction. Now Snell's law actually gives a very good idea of the refractive angle and the angle of incidence and how they are linked with the refractive indices of two medium. So let's take the N1 be the refractive index of the medium of incidence and I1 is the angle of incidence, and similarly N2 be the refractive index of in the second medium, and I2 is the angle of refraction. According to Snell's law, N1 sine I1 is equal to N2 sine I2. So for all refraction happening, this condition is satisfied. Any discussion with refraction also necessitates the mention of critical angle. So what is critical angle? Now, when we think of refraction ray or even the incident ray, so let's take a case. Well, the ray is going from a denser to rarer medium. What we have studied till now, it suggests that the ray will deviate away from the normal. Now for a particular value of the angle of incidence, this ray will just graze perpendicular to the point of separation between these two media. That means no refracted ray will enter the medium of refraction or the rarer medium. This is known as a critical angle. Now if we go a notch up, that is higher up than the critical angle, then the ray will be totally internally reflected. That is, it will come back to the medium of incidence and no ray will go to the second medium. Now, total internal reflection is of important use in biology.
So what are the uses of total internal reflection in biology?
The uses of total internal reflection in biology is manifold. One of the prime example is a problem. The problem in light microscopy is too much light. Let's say if I want to see events at the surface of the cell, then if I just use a light microscope, the whole of the cell is light enough. If I use a microscope or a lens where I do the condition of total internal reflection, then only a part of the whole cell which is near the plasma membrane will get lightened up. I will come to the details in later section of this lecture. Now moving forward, another phenomena when light interacts with matter is dispersion. So what is it? Now if you pass light through a prism, and if we are talking of polychromatic light, that is light made up of different wavelengths and different colors, then what happens is while passing through that prism and while it emanates from the other side of the prism, light gets split into its different color. This happens again because the wavelength of light comprising of the white light is different. This phenomena is known as dispersion. Dispersion actually helps you to see the colors of the rainbow. Now coming to another phenomena when light interacts with matter is diffraction of light. So what is diffraction? Diffraction is bending of light when it hits an object. Now there's a small criteria which has to be fulfilled for light to be diffracted by that object. The size of the object should be comparable to the wavelength of incident light. Then only it will get diffracted. Now, diffraction of light actually can result in formation of new wavelets of lights. If we are talking of different rays which are getting diffracted, because they are going into different directions, they now will interact with each other, leading to what is known as interference patterns. Now, if both the waves are in phase, that is, both the interacting waves have their crest and trough matching, this interference will give rise to increase in the intensity of light, because we know that I is proportional to square of amplitude. It's not that when always waves interfere, there is an increase in amplitude. If two waves are out of phase such that they're out of phase by value lambda by 2, which is the wavelength by half of the wavelength, then destructive interference may happen, due to which you may not see even any light emanating. So one of the pioneering experiment which was done to prove such interference patterns was by Young, which is known as the Young's double slit experiment. In this experiment, we used monochromatic light, which was allowed to pass through two small slits and then focused on a screen. It was seen that wave patterns were formed from those points or small slits, and these were interacting with each other, giving rise to some regions which were intense and some region where there was no light. This Young's double slit experiment also proved that light is wave in nature.
Sir, I have a question. Can it be observed with polychromatic or white light?
Yes, it can be observed with polychromatic light. Let's perform an experiment. So we can dim the lights and let's see. Thank you for the adjustment. Now coming to the experiment with polychromatic light, we have used a torchlight, which is a polychromatic light, and we have used a cardboard having two holes near to each other. Now look at the screen, which is the white paper in our case, and you will see concentric rings between which there are dark regions which indicate destructive interference, and the periphery of the rings are quite bright, which indicate constructive interference patterns. Another aspect of light which is important when light interacts with matter is polarization. So what is polarization? As I have discussed before, that the electrical vectors of light vibrate in different directions. Now do consider that I'm not thinking of one ray of light. It's a rays of light emanating from the source. So if I want all the electrical vectors to vibrate in the same plane, then I have to cut off the vectors which vibrate in other planes. So I need a polarizer, and the polarizer is such an instrument which can be a glass which is specially covered, which can help you cut off all these lights or vectors which vibrate in other directions. Now, depending on which plane you are polarizing, light can be plane polarized or S-polarized. Similarly, if we can polarize using a circular polarizer, then light is also known as circularly polarized light.
Sir, what are the uses of polarized light?
The uses of polarized light, especially in biology, can be observed if we study what is optical birefringence. Now, optical birefringence is normally defined as double refraction of light in a transparent, molecularly ordered material, which is manifested by the existence of anisotropic substances having definite crystal axes.
So what is an anisotropic substance?
An anisotropic substance is such where the different faces have different axes. So let's take an example. An isotropic substances, when light enters, it will get refracted in a similar manner from each of the face. But in anisotropic substance, where there is some changes in each of the faces, the refraction will not be similar from each faces. Now, this can be utilized in biology. If there is any inherent anisotropy present in any of the biological substance, especially substances which are present in the membrane, then it can be observed by using light which is polarized. Now, how we do that? This is mainly by giving light in a defined optical axis. If there is anisotropy present, then it will get deviated from that optical axis. Now, light, if it have a proper wavelength and proper energy content, can also be absorbed by the interacting substances. Now, I again reiterate, the criteria for absorption is that the energy of light should be sufficient that it transfer the electrons of atoms in the ground state to its excited state. This phenomena is known as absorption. Due to absorption of light, if I look at the light spectrum, certain wavelengths will not be visible because it has already been incorporated into the interacting substance. Another phenomena which happens after absorption is fluorescence. Now, fluorescence is not present in all molecules. There's a criteria for a molecule to have fluorescence. First, it should absorb light. Second, there should be sufficient energy difference between the ground state and the excited state of the atoms, so that when the electron again comes back to its ground state, it releases the energy in form of photon. Now, another important aspect to remember during fluorescence is a time span. It happens within 10 to the power minus 12 to 10 to the power minus 9 seconds. So such is the low time span. Now, along with fluorescence, there is another phenomena which can happen to certain molecules. That is, after the absorption, the electron goes to its excited state. Then rather than coming to the ground state, it can hover into a triplet or a metastable state. It can stay there for some time and then come down to its ground state, releasing the energy in form of photon, but that phenomena is known as phosphorescence. Now, the time span for phosphorescence can vary from 10 to the power minus 5 seconds to 10 to the power minus 2 seconds.
So here I have a question. Why is the wavelength of emitted light longer than the incident radiation?
Good one. Let's look at the figure. Now, if you see, when light is absorbed, the photon is utilized to take the electron from its ground electronic state to its highest electronic state. So some energy has been utilized. Now, while coming back to the ground state, you will see that some of the energy is lost in form of vibration relaxation, and then when it comes to the lowest vibration level of the excited state, it jumps to the ground state, releasing the energy in form of photon. So if E is equal to hc by lambda, then you will see the energy content of the incident light will always be greater than energy content of the emitted light, in our case the fluorescence. Now, because there's an inverse relationship with frequency and wavelength, hence we can also say that the wavelength of the emitted light is greater than the wavelength of the incident radiation. Now, coming how light is perceived by human eye. Now, what an eye can detect is actually difference in the intensities of light, which is known as contrast. That is, the intensity of light from an object versus the intensity of light from the surrounding medium. It is this contrast which can vary depending on high light or low light conditions. In high light conditions, it is the cone cells which can actually perceive light. They can also detect the color of light. However, the vision which is required for low light condition is actually guided by the rod cells which are present in our eye. So to summarize, in this lecture we have discussed about the nature of light, the different qualities of light, the properties of light when light interacts with matter, and lastly how we perceive light. Thank you.